viewers, welcome to the lecture series of Food Science and Technology. The present lecture on the topic entitled Colorimeter. This topic comprises with the following 5 sections: Introduction, Basic Principle, Instrumentation and Methodology, Applications and Conclusion. Introduction. In physical and analytical chemistry, colorimetry is a technique used to determine the concentration of colored compounds in solution. A colorimeter is a device used to test the concentration of solution by measuring its absorbance in a specific wavelength of light. To use the colorimeter, different solutions must be made, including a control or reference of known concentration. The color or wavelength of the filter chosen for the colorimeter is extremely important, as the wavelength of light that is transmitted by the colorimeter has to be the same as that of absorbed by the substance being measured. A colorimeter is a light sensitive device used for measuring the transmittance and absorbance of light passing through a liquid sample. The device measured the intensity or concentration of the color that develops upon introducing a specific reagent into a solution. There are two types of colorimeters: color densitometer, which measures the density of primary colors, and color photometer, which measures the color reflection and transmission. Color is the attribute of visual perception consisting of any combination of chromatic and achromatic content. This attribute can be described by chromatic color names such as yellow, orange, brown, red, pink, green, blue, purple, etc., or by achromatic colors names such as white, grey, black, etc., and qualified by bright, dim, light, dark, or by combination of such names. Perceived color depends on the spectral distribution of the color stimulus, on the size, shape, structure and surrounding of the stimulus area, on the state of adaptations of the observer's visual system, and on the person's experience of prevailing and similar situations of observations. Let us see the basic principle of colorimeter. The colorimeter is based on the Beer-Lambert's law, according to which the absorption of light transmitted through the medium is directly proportional to the medium concentration. In colorimeter, a beam of light with a specific wavelength is passed through a solution via a series of lenses which navigate the colored light to the measuring device. This analyzes the color compared to existing standard. A microprocessor then calculates the absorbance or percentage of transmittance. If the concentration of the solution is greater, more light will be absorbed, which can be identified by measuring the difference between the amount of light at its origin and after passing through the solution. In order to determine the concentration of an unknown sample, several sample solutions of a known concentration are first prepared and tested. The concentrations are then plotted on a graph against absorbance, thereby generating a calibration curve. The results of the unknown sample are compared to that of the known sample on the curve to measure the concentration. Beer-Lambert's law. According to Beer-Lambert's law, when monochromatic light passes through the colored solution, the amount of light transmitted decreases exponentially with the increase in the concentration of colored substance. That is, IT is equal to I naught e to the power of minus kc. Lambert's law. According to Lambert's law, the amount of light transmitted decreases exponentially with increased thickness of colored solution. IT is equal to I naught e to the power of minus kt. Therefore, together Beer-Lambert's law is IE divided by I naught is equal to e to the power of minus kct, where IE is intensity of emerging light, I naught is intensity of incident light, E is base of neutral logarithmic exponential function, K is a constant, C concentration, T is thickness of the solution. Instrument and methodology. Operators. The instrument used to measure color is colorimeter. This apparatus will comprise of the following parts: light source, filter, the device that select this desired wavelength, cuvette, chamber, the transmitted light passes through compartment wherein the solution containing the colored solution are kept in cuvette made of glass or disposable plastic. Detector. This is a photosensitive element that converts light into electrical signals. Galvanometer, measuring electrical signal quantitatively. Steps for operating the photoelectric colorimeter. Chooses the glass filter recommended in the procedure and insert the glass filter. Fill 2 of the cuvette with blank solution to about 3/4 and place it in the cuvette slot. Switch on the instrument and allow it to stabilize for 4 to 5 minutes. Adjust to 0 optical density. Take the test solution in another cuvette and read the optical density. Take the standard solution in varying concentration and note down the optical density as S1, S2, S3, S4, S5 and so on. Plot a graph by taking concentration of standard solution versus optical density. From the graph, the concentration of the test solution or unknown solution can be calculated. Color and illuminance measurement. In many applications involving the measurement of color or the color temperature of self-emitting light sources, the same measurement geometry is used as for illuminance. Appropriate absolute calibration of the measuring system allows the illuminance of reference plane in lux to be determined in addition to the colorimetric parameters. If the incident light is falling diffusely, this measurement requires the measuring system to have a field of view adapted to the cosine function. Only in this way the loss for the incident of diffuse radiation from one or more sources of radiation can be satisfied. Detectors used to determine absolute impedance must therefore have a cosine spatial function as their measurement geometry. If the incident radiation is not parallel, the accuracy of the cosine function is critically important to the result of measurement. Classifies the quality of devices for measuring illuminance, also called as luxometer or photometer, according to the accuracy of their measurement into devices of class A with a total uncertainty of measurement of 7.5% for precise measurements. Devices of class B with a total uncertainty of measurements of 10% for operating measurements. Design of colorimeter. The three main components of a colorimeter are a light source, a cuvette containing the sample solution and the photocell for the detecting the light passed through the solution. The instrument is also equipped with either colored filter or specific LEDs to generate colors. The output from the colorimeter may be displayed by an analog or digital meter in terms of transmittance or absorbance. In addition, a colorimeter may be contain a voltage regulator for protecting the instrument from the fluctuations in main voltage. Some colorimeters are portable and useful of on-site tests, while other are large benchtop instrument used for laboratory testing. Application of colorimeter. Colorimeters are widely used to monitor the growth of the bacterial or yeast culture. They provide reliable and highly accurate results when used for the assessment of color in bird plumage. They are used to measure the monitor the color in various foods and beverages, including vegetable products and sugar. Certain colorimeters can measure the color that are used in photocopy machine, fax machine and printers. Colorimetric method for the estimation of glucose in solution. One useful and often used way of obtaining concentration of chemicals in a solution, if it has a color, is by colorimetric method. If the analyte is not colored, an appropriate reagent must be added that reacts with the analyte to produce a colored compound. In this experiment, the method for determining the concentration of sugar is based upon the color that forms when sugar reduces 3,5-dinitrosalicylic acid to 3-amino-5-nitrosalicylic acid. This method tests for presence of free carbonyl group, so called reducing sugars. This involves the oxidation of aldehyde functional group present in, for example, glucose and ketone functional groups in fructose. Simultaneously, 3,5-dinitrosalicylic acid is reduced to 3-amino 5-nitrosalicylic acid under alkaline conditions. Oxidation of aldehyde group into carboxylic group and reduction of 3,5-dinitrosalicylic acid to 3-amino-5-nitrosalicylic acid. In this experiment, sucrose is provided, which is the non-reducing sugar, does not undergo reaction with the 3,5-dinitrosalicylic acid. Therefore, the sucrose and complex carbohydrate must be broken down into simple sugars like glucose first. The hydrolysis can be done by boiling the sample with hydrochloric acid, and then the pH is adjusted to give a basic solution under which the conditions are good for reducing sugars. This method is a straightforward modification of the original DNS method for glucose analysis. The sugar in the soft drink are at too high concentration for this method, so dilution must be carried out before carrying out analysis. The measurement of transmittance is made by determining the ratio of the intensity of incident and transmitted light passing through pure solvent and sample solutions as a function of wavelength. The logarithm of the reciprocal of the transmittance is called the absorbance. The equation of absorbance is equal to A is equal to log of 1 by T. According to Beer's law, the absorbance of solution should be 0 if there is none of the absorbing species present in solution. A blank solution that does not contain analyte being analyzed but have the same composition as the solution can be used to calibrate the machine into 0 reading absorbance. Then the machine can be used to find concentration of other solution. Beers-Lambert's law is only obeyed when the standard curve is linear for reasonably dilute solution. Let us see the procedure for the estimation of glucose. Preparation of sucrose standard solution. Prepare 1000 mg per liter of standard solution by suitable dilution of stock solution. 2:10 dilution of stock solution as follows: 2 ml of the stock solution pipette into a clean 10 ml test tube and add distilled water to calibrate the mark of 10 ml. Cover the tube and shake well to mix. In a similar fashion, prepare 4, 6 and 8 ml dilutions in 10 ml of standard flask. Prepare 5 standard from the original stock solution and the 4 dilutions as follows. Pipette out 2 ml of each sucrose standard solution into test tubes. Add 2 ml of 6 molar HCl into each test tube and place it in a boiling water bath for 10 minutes. The test tubes are removed carefully. Pipette 0.8 ml of 2.5 molar sodium hydroxide, 2 ml of 0.005 molar of 3,5-dinitrosalicylic acid into each test tube. Then place the test tube in a boiling water bath for 5 minutes. Set the timer when the tubes placed in the hot water so that each tube to stay in the water for the same amount of time. Remove the test tubes from the boiling water bath at the proper time and quickly place it in ice water bath for 10 minutes. Wash the cuvette with some of the blank or distilled water solution and dry cuvette and then place the 80% solution filled cuvette into the spectrophotometer. The measurement of the standard solution was taken and the absorbance was recorded. Preparation of unknown sample solutions like beverages. Dilution of beverages were prepared as follows: 0.1, 0.2, 0.4, 0.6 and 0.7 in a series of 100 ml standard flask. Treated 2 ml of liquids of the diluted samples in the same manner that you did for the standards. Record the absorbance for the diluted samples. Next, determination of phosphate enzymes in plants. Phosphatase enzymes are widespread in nature and may be easily extracted from germinating seeds. They serve to remove phosphate groups from a wide range of organic phosphates and thus make available a metabolic pool of phosphate ion. The accurate estimation of phosphate in a complex process, so this protocol relies a substrate which yields a product which is easily quantified by colorimetric methods. Phenolphthalein phosphate has the property of being colorless in alkaline solution, whereas free phenolphthalein produces a pink color. The amount of enzymatic activity can thus be estimated by the intensity of color produced from a standard reaction mixture when sodium carbonate solution is added. The phosphatase enzyme has an optimum pH of around 5, so the pH of the reaction should be kept below 9.2. Any buffer system can be used, including the buffer tablets. The practical makes use of basic laboratory apparatus, although you may need a borrow of colorimeter from the chemist. Since the reaction is stopped by the sodium carbonate, the tubes can be stored in the refrigerator for several days before the color intensity is assessed. This can also be used for reassessment of the accuracy of the technique. If the duplicate are done for each variable under investigation, the colorimeter reading for each pair should be identical. Next application, determination of iron in food products. Some metal ions in very low concentration show the strong color by the formation of the complex with ligand. These complexes are the result of the interactions of a Lewis acid and Lewis base. The ideal color forming reagent should be stable, selective, and react rapidly to form soluble, highly colored complexes. The colored complex should have a high absorptivity and be free from variations in color due to minor changes in pH or temperature. In general, organic colorimetric reagents are considerably more sensitive than inorganic ones. They give more intense colors and are therefore frequently used for trace analysis. With many organic reagents, it is possible to determine concentrations at the ppm level. 2,2-bipyridyl forms an intensely red complex with ferrous ion, that means iron 2, which may be exploited to determine iron concentration in the ppm range. The reaction is 3-bipyridyl with Fe2 plus gives the complex of Fe-bipyridyl 3 complex. The complex conforms to an octahedral geometry with coordinate covalent bond being formed between the adjacent sp3d2 hybrid orbitals of the Fe2 plus. The complex forms rapidly, stable over the pH range 3 to 9 and may be used to determine iron 2 concentrations in the range of 0.5 to 8 ppm. If the sample contains ferric forms, then it must be reduced to iron 2 to produce the colored species. A suitable reagent for this purpose is hydroxylamine hydrochloride. The concentration of iron in the sample could be calculated from Beer's law. However, in this procedure we employ a different method. We will prepare a standard solutions and compare absorbance reading of the sample and standard solution. This technique minimizes the effect of instrument and solution variation. Let us see the experimental procedure. Preparation of original iron solution. To an accuracy of plus or minus 0.1 milligram, weigh out N of ferrous ammonium sulfate to prepare 250 ml of solution, which is 0.002 molar with respect to that of compound. Quantitatively transfer the salt into a 250 ml volumetric flask, add sufficient water to dissolve the salt and add 8 ml of 3 molar sulfuric acid, dilute it to the mark with distilled water and mix well. We shall call this the stock iron solution. Pipette 10 ml of this solution into 100 ml volumetric flask, add 4 ml of 3 molar sulfuric acid and dilute it to the mark with the distilled water and mix well. Label this solution as original iron solution and calculate the concentration of iron in ppm in this solution. Determination of the absorbance of standard iron solution. Before beginning this part of the procedure, be sure to record the number of the colorimeter that you are using for this part of the analysis. The number of the colorimeter is found on a small blue tag on the front of the colorimeter. Further, absorbance measurement must be made with the same colorimeter and the same cuvettes in order for this method to work. Label the solution containing the iron as a standard iron solution and calculate its iron concentration in ppm. Determine the absorbance of these solutions at the wavelength of maximum absorbance previously determined. For a blank, use the solution which does not contain iron. Make at least 3 measurements. In each case, reset the 0 and 100% transmission. Record both the percent transmission and absorbance value. Empty your cuvette and refill it with the another portion of the same solution, and again determine the absorbance value. Calculate the average of all 6 absorbance values. Analysis of iron unknown. Clean a 100 ml volumetric flask, pipette 10 ml of unknown solution into it, and then add 4 ml of 3 molar sulfuric acid, mix well, and then make up to the calibration mark with the distilled water. Mix well by inverting and shaking the stopper flask. Pipette 10 ml of these solutions into a 50 ml of volumetric flask, and then in this exact order 1 ml of 10% hydroxylamine hydrochloride solution, 10 ml of 0.1% bipyridine solution, and 4 ml of 10% sodium acetate solution. Be sure to mix well after the addition of each reagent by gently shaking or swirling, but not inverting the flask. After all, the reagent have been added to fill the flask to the mark with the distilled water and mix well by inverting and shaking. Determine the absorbance of this solution using the previous blank solution as the reference and the wavelength of the maximum absorbance determined earlier. Measure the absorbance at least 3 times, empty the cuvette and refill it with another portion of solution, and again determine the absorbance. Conclusion: a colorimeter is generally any tool that characterizes color samples to provide an objective measure of color characteristics. The colorimeter is an apparatus that allows the absorbance of a solution at a particular frequency of visual light to be determined. Colorimeters hence make it possible to ascertain the concentration of a known solute, since it is proportional to the absorbance. The difference in the amount of monochromatic light transmitted through a colorless sample and the amount of monochromatic light transmitted through a test sample is a measurement of the amount of monochromatic light absorbed by the sample. In most colorimetric tests, the amount of monochromatic light absorbed is directly proportional to the concentration of analyte. However, for a few tests, the relationship is reversed and the amount of monochromatic light absorbed is inversely proportional to the concentration of the test factor. Colorimeter extensively used in the food and beverages industries to maintain required minerals like iron, phosphate, dyes in food materials. Thank you.